Okay, we're going live. We are live. So hello everyone and welcome back to the Latin American webinars in physics. I am Joel Jones from the PUCP in Peru, and I will be your host today. On this day, we are having a colloquium. I don't know what happened in 2023 and 2024. We just forgot about them, but now the colloquia are back. So today we have a super relevant topic for the 21st century, which is sustainability, and specifically sustainability in science. And to learn about this, we have Pete Millington, who is a senior research fellow at the University of Manchester, as well as UK Research and Innovation Future Leaders Fellow. Let me tell you a bit more about Pete. He started his PhD in Manchester itself, which was then followed by a postdoc at the University of Sheffield. Then, after a joint postdoc at Manchester and the IPPP in Durham, Pete got a TU Foundation Fellowship at the Technical University in Munich, and then a fellowship at the University of Nottingham. Now back in Manchester, and apart from worrying about sustainability, Pete works in applications of quantum field theory, in cosmology, astroparticles, and high-energy physics, emphasizing on scalar tensor theories of gravity and pseudo-Hermitian quantum mechanics. Well, it is likely we'll invite him again for a talk about those topics in the future. Anyway, before we begin, let me remind all viewers that you can ask questions and make comments via the YouTube live chat system. And these questions, as usual, will be passed on to Pete at the end of the talk. So, Pete, we're all yours.
I'll just start sharing my slides. Hopefully everybody can see that. Thanks for that super introduction, and thank you all for logging on and joining to listen to what I have to say. So the topic of this colloquium is finding a sustainable science, and this is a difficult topic, and I'm going to focus very much on the big picture and not so much the technical details, but I have left a list of references that hopefully will be posted alongside the video in case you want to look a little bit further. So to get us started, and I'm just going to have to put the video out the way. There we go. The bottom line is that the climate crisis is here. And what I put on this first slide is an excerpt from the 2023 synthesis report from the Intergovernmental Panel on Climate Change. And what they say is that human activities, principally through emissions of greenhouse gases, have unequivocally caused global warming, with global surface temperature reaching 1.1 degrees centigrade above 1850 to 1900 in the years 2011 to 2022. Global greenhouse gas emissions have continued to increase, with unequal historical and ongoing contributions arising from unsustainable energy use, and land use change, lifestyles and patterns of consumption, and production across regions, between and within countries, and among individuals. And this is a statement that the IPCC makes with high confidence. But the other thing that's important to acknowledge is that it's not fair. And the IPCC is very clear about this point, that widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. Human-caused climate change is already affecting many weather and climate extremes in every region across the globe. This has led to widespread adverse impacts and related losses and damages to nature and people, again with high confidence. And vulnerable communities who have historically contributed the least to current climate change are disproportionately affected. And again, this is a statement made with high confidence. So this is the statement of the situation that we find ourselves in. And the problem is we're not on track. If we look at the rate at which greenhouse gas emissions need to reduce in order to meet, for instance, the Paris goals of limiting warming to less than 1.5 degrees centigrade, then we need to halve emissions in the next 16 years. And as you can see from this figure, based on implemented policies, we're a very long way away from where we need to be. But I don't want to dwell so much on the bad news. What I want to try and be in this talk is more forward-looking and optimistic. But before I do that, I think it's probably important for me to answer this question. Who do I think I am? And that's in the sense of, who am I to be talking about sustainability? And I think this gets to the bottom of a really important question in general, which is, who gets to talk about sustainability? And for me, at least, the bottom line is everyone. It affects everyone, and it's a conversation that everyone needs to be a part of. So who do I think I am? Where am I coming at on this issue of sustainability? Well, what I'm going to talk about for the rest of this talk is really my perspective as a theoretical physicist working in high energy physics, cosmology, and astroparticle physics. And I'm going to use the acronym HECAP just to cover all of those. Now, one of the things that's really important for me to acknowledge as well is not only that I'm a theoretical physicist, but also that I'm a theoretical physicist in a position of very real privilege. And that, I think, is an extremely important thing to acknowledge when coming at topics like sustainability, where climate injustice is a very real and serious factor. So, thinking like a theoretical physicist, I used to think that I solve hard problems, that theoretical physics was difficult and the problems were tricky. But actually, when I started thinking about sustainability, well, sustainability really is a hard problem, and it's hard in a very different way. And this made me think about the way that I do science and the way that I do theoretical physics. And I realized that actually I don't solve hard problems because hard problems are too difficult to solve. What I do instead is I make approximations, or I find simple proxies, simple analogs to problems, and I solve them. And that's the classic joke of a spherical cow in a vacuum. This is the way that we do theoretical physics. And what I learned when I started trying to educate myself about the sustainability space was that what everybody else calls those type of problems is tame problems. And these tame problems that we have in mathematics and theoretical physics, they're to be contrasted with what the climate crisis is. And the climate crisis is a wicked problem. And this term was coined by Rittel and Weber down in 1973 at the bottom there. So what is a wicked problem? Well, a wicked problem is one with no definitive formulation. It's one with no stopping rule. You don't know when you've solved the problem. It's not about true or false, but it's about good or bad when it comes to solutions. And the problem is that we can't test those solutions. We don't know whether they're good or not. And so there's no trial and error. We get one shot. We get one attempt at solving a wicked problem. And there's an innumerable set of solutions. There's all manner of ways that we can tackle a wicked problem. They're also essentially unique. And they're almost invariably a symptom of other problems. And that's certainly the case for the climate crisis. They have numerous representations. We can present those problems in different ways. And this is really the key thing, this number 10, that there's no right to be wrong. We're not allowed to get the solutions wrong. In physics, as long as we follow the right rules and we come to some conclusion, then that's a valid conclusion to reach. But that's not the case for wicked problems. It's not just about the rules. It's about the solution that you present. And this is what the climate crisis is. It's a wicked problem. And part of this is the fact that it's a truly interdisciplinary problem. It relies on science and technology, engineering, mathematics, medicine, the STEM subjects. But it also relies on economics, politics, sociology, law, and many other things. So the solution space is extremely complicated. It's a multifaceted, interdisciplinary problem. So what about us in high energy physics, cosmology, astroparticle physics, and related disciplines that rely on similar technology, similar infrastructure? What is our part to play in this? Where does sustainability feature in our activities, and how does it affect our activities? And here I just wanted to put a warning, and the warning when we hit these conversations is about climate whataboutery. So how do we take this situation and look at it from the lens of the research that we do and the research practices that we're engaged in? Well, first of all, I think it's important to acknowledge that we have a moral and pragmatic reason to act. Firstly, as scientifically literate citizens, we have a responsibility to lead by example and limit our negative environmental impacts. We have that scientific literacy. We have an appreciation for the data and the implications that that data has that's been collected over many years by our colleagues in environmental and climate science. And we're scientists. But from a pragmatic point of view, if we believe that our science is of value to society, and I absolutely do, then we want to be allowed to keep doing it in the face of additional constraints, in terms of additional scrutiny from the public, from government, from funders, about the way in which we're undertaking our research and the impacts that that research has. And this was another buzzword that I learned when trying to move into this sustainability space. And that's this idea of a social license to operate. And that social license to operate, the mandate that we're given to do the science that we want to do, and the freedom to drive that science in the directions that we drive it, that social license to operate is a fragile privilege. And just like trust, it's hard to gain and easy to lose. And ultimately, this is where accountability comes in. The public, funders, and governments entrust us as scientists with financial and material resources, and we're accountable for how we use them. Now, in the past, that accountability might just have gone as far as effective use of money. But the situation is very different when we start thinking about sustainability. And what this means is that we need to take ownership of both our positive and negative externalities. So again, another buzzword. So an externality just being a cost or benefit that's caused by one party on another. So what are the things that result from our science that are a benefit to society? And what are the things from our science that are a cost to society? And if we think about our negative externalities, the things that have a negative impact, a cost on society, we can look at, for instance, emissions. And our emissions are too high. We're not alone in having emissions that are too high, but the emissions that come from the research that we do are too high. And this figure is taken from the Sustainable HECAP Plus reflective document, which I'll talk about shortly. And it's a collection of data that is self-reported. It's self-reported data from institutional reports. And the thing to be said before the caveat to be said before I go into any more detail on this plot is that there is some selection bias in this self-reporting. Only institutions that have chosen to do this have reported this data. The data is not necessarily complete, and CERN is possibly the example on here with closest to complete estimations of emissions from Scope 3 emissions, which I'll qualify in a minute. And these are only for a particular year, and so I'll give some additional clarifications as we go on. But what we see on this plot is the emissions from various institutes and research facilities broken down by scope. So scope 1 is direct emissions. So in the case of particle physics, you could think about the loss of high global warming potential gases like fluorinated gases. The orange, that's scope 2 emissions, so the next bar to the right. And that's emissions from purchased electricity, essentially. And then the final band to the left, to the right rather, the green band, this is scope 3 emissions. So you can think of this as supply chain, things like procurement, food, waste treatment, and travel. And the data here has been divided by the number of researchers making use of those facilities or working at those institutes. And what you see is if we divide it in that way, if we take ownership in that sense, then all of these emissions exceed the budget that we have to 2050 to meet the Paris goal of limiting global warming to less than 1.5 degrees. But many of these also exceed the global average for emissions. The other things to note is that, so the CERN numbers here are during LHC shutdown. When LHC is running, the scope 2 emissions are roughly double what they are here. The other thing that you can see in the CERN numbers is how significant the contribution to emissions is from procurement. And I'll mention CERN's new environmentally responsible procurement policy later. You also see a major disparity in the scope 2 emissions, or scope 1 and 2 emissions combined for Fermilab and LANL compared to CERN. And this is essentially down to the energy mix going in to that infrastructure. So CERN's electricity is purchased predominantly from France, and France has a high share of low carbon nuclear power. If you were to estimate this based on the European average, then I think roughly an order 5 factor bigger you would see in the scope 2 emissions on the European grid on average. So our emissions are too high. We're using more of the carbon budget than we should be. But the other thing that I think is important to acknowledge is that our emissions profile is different to the global emissions profile. So globally, and that's what's represented on the left here, energy and agriculture, forestry and land use. So food production and energy are essentially the dominant sources of CO2 emissions or CO2 equivalent emissions globally. Whereas what we see in the emissions from, and here the example given is CERN, is that a huge proportion of those emissions are down to procurement. A large proportion is down to loss of high global warming potential gases, and then a large contribution from electricity, and then mobility below that. So the profile of our emissions is not representative of the global profile of emissions. And this means that when we're thinking about sustainability in terms of our research practices, we have to take both of these pie charts into account. There are things that we can affect positively that are a big slice of the pie chart on the right, a big slice of the contributions from our emissions. But then we should also be addressing those things which are a contribution to a very big slice of the pie globally. And the other thing to bear in mind is that fields like high energy particle physics and astronomy, for instance, where we have large amounts of data processing, where in the case of particle physics, we have energy hungry facilities. In the future, energy is going to be scarce and expensive. And again, this is going to present a challenge from a pragmatic perspective for us doing the type of research that we want to do. Now, if we want to meet the Paris climate goal, we have to rapidly reduce reliance on fossil fuels, and that has to be replaced by something. And if we extrapolate the growth in energy consumption forward in time, what this leaves is this huge energy gap. Now, some of that can be mitigated through reduction in demand, through efficiency, but that's not going to be enough. We need to do more. So now turning to this document that I mentioned, and this is really where I personally came into sustainability properly. Now, this document, Environmental Sustainability in Basic Research, a Perspective from ECAP+, this document started as a grassroots initiative, which was conceived in the 2021 Sustainable HEP workshop, so the first of this successful series of online workshops focused on sustainability in high energy physics and related disciplines. And the aim was, exactly as it says here, to reflect on sustainability in the context of our research, and to do so very broadly. And what that means is actually, although this is framed from the direction of high energy physics and cosmology and astroparticle physics, but also hadron and nuclear physics, who all rely on very similar infrastructure and face similar problems in terms of computing and sustainability. Actually, a lot of the things discussed in this document are relevant across big science in general. So the archive link is there, and I invite anybody who's interested to read it, and it will appear in JINST very, very soon. The other thing to say is, of course, that there are lots of other sources available, and I've just listed a few here, and that you might be interested to take a look at. So how did we approach this problem? Well, we took a holistic approach, and this was really inspired by the environmental reports coming out of institutions, which really looked across all aspects of working processes and estates infrastructure, and then scientific infrastructure. So the areas of focus for the document were computing, so thinking about hardware implementation, about software implementation, the construction of data centers, thinking about energy in terms of sources, energy saving, ways of recuperating energy, for instance, through reusing waste heat from data centers, thinking about food in terms of conference catering and canteens, mobility, thinking about commuting, conference and business travel, the way in which we manage collaborations in science, thinking about research infrastructure and technology with a real focus on life cycle assessment, which I'll come back to shortly, and a focus on F gases, so gases with very high global warming potential. And then resources and waste, and of particular concern for what we do, consumables, e-waste. And within each of those areas of focus, we really looked to think about concrete recommendations, to be proactive, things that we could actually do to move the field forward. And these were targeted at individual level, things that all of us can do, things at group level, so the level of collaborations or individual research groups, and then at the level of institutions, so universities, research institutes, funders. And I'm not actually going to go through all of those recommendations in this talk, but I invite you to go and have a look through the documents. But the key thing is that there is no one-size-fits-all solution for how we should do things better. And this goes back to the points that I was saying before, that sustainability is the climate crisis, addressing sustainability. This is one of these wicked problems. And it's multifaceted and interdisciplinary, and it relies on a huge number of factors and involves a huge number of stakeholders. So sustainability is really a systems problem. And this means that any recommendations that we make, they have to be seen through a local lens. We have to look at the systems in which we're trying to affect these positive changes. So the things that need to be done in say, Europe and America versus elsewhere in the world may be very, very different. And this is, I think, a really, really important point that we need to bear in mind when we're thinking about the sustainability of our research field. And related to that point is that environmental sustainability and equity can be in tension with one another. And an example here is limiting business air travel. And on the positive side, obviously, limiting business air travel reduces emissions. So it's good for environmental sustainability, but there are many negatives in relation to equity. So it's all well and good in, say, Europe, where it's reasonably easy to get between institutes by train. It might be okay to implement these sorts of policies. But what you risk more on a global scale is further entrenching geographic disparities, further distancing and isolating people from main hubs of activity, for instance, CERN. This can have disproportionate impacts on career progression. So all of those whose careers are established, perhaps they have less of a need to network because those networks are already established. But early career scientists who are trying to build those scientific networks, who are trying to get that exposure to disseminate their research, then these sorts of policies can have a disproportionate impact. And it can have a disproportionate impact on those who are unable to take longer trips, for instance, those with caring responsibilities. Now, of course, a move to remote working, to virtual conferencing, webinars like this one, it allows that reach, and there are benefits to that. But this balance between achieving greater environmental sustainability, but also greater equity within our fields of research is a very real challenge. So the conclusion of the HECAP Plus document was that assessing, reporting on, defining targets for, and undertaking coordinate efforts to limit our negative impacts on the world's climate and ecosystems must become an integral part of how we plan and undertake all aspects of our research. And one example of how that can be done, so this is just one of the recommendations that I will talk about from the Sustainable HECAP Plus document, is that life cycle assessment should be standard practice in what we do. So life cycle assessment is just the assessment of the environmental impact of a project over its entire life cycle. So from cradle to grave. So this goes from the level of resource extraction through to processing those resources, the manufacture and construction, the operation of facilities, their decommissioning, their disposal, and going round if any of that is then recycled. And obviously at all points in here, there's a question about transportation. So the aim of a life cycle assessment is really to look at all of these pathways in a project to determine the overall environmental impact in terms of emissions, but also in terms of hazardous waste and effluents to the environment. But all of these things that I've mentioned, this is only a start. A lot of these things are ways of fixing things that we currently do. And the question is, do we need to go further? Is it time to keep driving our field toward a social tipping point? A point where these continued small changes trigger a more rapid shift in the social norms within our field. I think very seriously, we have to ask ourselves the question, all of these things that I've just talked about, these ways of fixing the activities that we currently do, is that enough? Or do we need to think more broadly about what a sustainable field looks like, what a sustainable science looks like? Now, there are good signs that this is happening. There are good signs, I think, that we're very close to one of these social tipping points in high energy physics and cosmology, in astroparticle physics, certainly in astronomy and other areas as well. And I've just summarized on this slide a few of those signs. So one of the things that we're starting to see within collaborations, within institutions, within funders, is the formation of governance structures to deal with sustainability. At the level of strategy, we're seeing sustainability featuring more and more prevalently in, for instance, the input process for the European strategy update in particle physics, where the ECFA guidance lists sustainability explicitly. Sustainability features in the SNOMAS process and in the P5 report in the US. There are strategies like the IGFA Sustainable Accelerators and Colliders strategy. So sustainability has been brought in strategically within the field. It's part of the forward thinking about how we're developing programs of research. In terms of process, we're seeing life cycle assessment adopted. So in 2023, partial life cycle assessment for ILC and CLIC was published. And the reference for that is in the list of references that hopefully will accompany this talk. LCAs have been undertaken by ESO and by the GRAND project. CERN has recently implemented environmentally responsible procurement policy to try to address the scale of those Scope 3 emissions. So again, we're seeing considerations of environmental impact folded into decision-making, policy, and procedures within the structural elements of the way in which big science works. We're seeing increased platforms for sustainability. This includes dedicated conferences like the Sustainable HEP series of conferences, which will be in its 4th edition this time round. But we're also seeing sustainability appearing in plenary talks and in parallel tracks in conferences as well. So ICHEP this year had a parallel track on sustainability and a plenary talk. And so now featuring very heavily within community events, we're seeing sustainability there alongside considerations in terms of equality, diversity, inclusivity, and accessibility. And this companionship is extremely important for all the points that I said before, that really sustainability and equity are two things that have to be tensioned very closely with one another. And then from the side of research, well, we're seeing dedicated research activity within these research fields. So, and I've just lifted a few examples here. So Le Boson Point 5, the CNRS funded and other funders in France program, which is a program of development of accounting tools, which now has a CERN plugin, which is extremely useful, as well as resources on sustainability. There's the Innovate for Sustainable Accelerating Systems program funded by Horizon Europe, looking, for instance, at energy recovery Linux, so more efficient designs for accelerators. There's ongoing activities and significant activities looking at reducing losses and uses of F gases in particle detectors, in cooling systems. And there's a lot of information about this, for instance, in the TDR2 for LHCb, which is also referenced in the list of references. F gases are particularly problematic because of their huge global warming potential, from factors of 1,000 to up to around 10,000 over a 100-year period for things like sulfur hexafluoride. And then substantial efforts in terms of green computing. So ways of running algorithms more efficiently, or designing Monte Carlo generators more efficiently, or attempts to and strategies to share data more freely, to allow greater reusability of data, to ensure that that data is not being reprocessed. And so all of this together, to me, points towards a huge level of optimism that sustainability is very much on the radar, very much in being incorporated in the way in which we're pushing the field forward. And so I go back to this question, are we ready to go further? Are we reaching a point where we can ask even more difficult questions about the way that we do the science that we want to do? And I think we are. I think we've got to this point. So there's two questions that I want to ask, two slightly more difficult questions. And one is, what can we achieve by addressing perverse incentives in science? We're in a situation where effectively everything is commoditized, and science is one of those things too. So we're increasingly driven by metrics. And those metrics have an impact on how people's careers develop and their incentives for instance, undertaking large amounts of travel and having to be hypermobile. It also feeds into an attitude of competition versus collaboration. Now, obviously, it's important to reproduce results and to cross-check results. But the question is, can that be done in an entirely collaborative way? or does it rely on competition? And the next question I wanted to ask is, what can we achieve by citing infrastructure differently? At the moment, fields like high energy physics, they're dominated by particular hubs because that's where the big infrastructure is. Whether it's Fermilab in the US, whether it's CERN in Europe, whether it's Keck. And the question is, can we do better by thinking about where we place infrastructure? And here, I think this also speaks to the two aspects that we have to deal with in a wider meaning of sustainability. On the side of climate, thinking about how we site infrastructure will allow us to perhaps build the next generation of infrastructure closer to sources of renewable energy. But also, it allows us to think about how we build a truly global science, a truly global endeavor in subjects like high energy physics, in cosmology, in astroparticle physics, and so on. Can this be used to help address systemic geographic disparities at the same time? And this sort of brings me to the end, because actually I didn't want to talk for too long, because I'm really keen for there to be lots of questions and discussion. So what does a truly sustainable, global, and equitable cutting edge science look like? How do we do the science that we believe to be important, the science that we know to be cutting edge? How do we do that same science, but how do we do it in a sustainable, global, and equitable way? And one of the things that I've hoped, I hope to have shown during this talk is that the process of getting to there is a challenging one, and we have to think about how we achieve this. How might we get to a truly sustainable, global, and equitable cutting edge science? So that's actually everything I wanted to say. So I'll stop there and answer any questions that people might have.
Okay, super. Thank you very much for the talk. So it was very eye-opening. So let's open the session for questions. Again, let's remind all our audience that you can make comments and questions on the YouTube live chat system. But let's start with the people who are currently around. I don't know if I have quite a couple of questions, but let's see if anybody else would like to begin. Maybe Roberto or Jacobo. Yeah, Roberto, go ahead.
Yeah, thanks. It was very interesting the talk, Peter. So I wanted to ask you about because something that caught my attention was the part when you referred to green computing, because I think in science or on modern, I also from the side of particle physics, we used to rely too heavy in computers in the sense that maybe all grants that the people apply is also to buy computers and change old computers that in principle are not so bad for doing the calculation, just take a little bit more, let's say. I mean, not going to the very big science like the data farms that could have CERN or something like that, but more or less saying that in the low scale physicists that is just few people all the time they are buying new computers. And in that sense, what do you expect for the policies related with these grants, kind of to include some issues like, let's say, like to refurbish all computers, recycling all computers, or something like that? Because in some sense, it's a lot of e-waste that we are creating in science, and not only in science, also in industry. I think it's the same in other fields.
Yeah, I think this is it's an excellent question, and so this is one of the things that's discussed quite a bit in the HECAP Plus document in terms of computing. But I think you've raised a really important point about things like refurbishment and reuse of computing, and this is essentially something that needs proceduralizing within institutions, right? There needs to be ways to repurpose computing, to buy computing that can be fixed rather than scrapped as soon as anything breaks. These sorts of considerations, so that the classic refuse, reuse, repair, recycle way of thinking about personal computing. But I think the other thing that your question touched on, which I think is really important as well, is about the incentives. Again, that we have to ask ourselves, what are the when we're putting together grant proposals, and we're asking for funding for things, we have to ask why we're asking for that funding, and it's certainly the case that there are incentives to max out the amount of funding that you can request, right? And I think these are the sorts of things, and the reason for that is because of the way we're measured as scientists. And so I think we have to think very hard about not just the technical, practical things that we can do, but also the structural changes that we can make to the way in which academic research, for instance, is how it works, how it's organized, how it's structured, what the governance processes are within academic research, how it's measured. Are the measures that we use commensurate with addressing things like sustainability, or do we have to adjust the measures that we use to make sure that they don't inadvertently incentivize things that have a negative impact? So I think, yeah, it's a great question. Thanks.
Thank you.
Following on that, because yeah, there are like two aspects here, right? So what is the impact that our large scale infrastructure has, and what is the impact that we as academics can have, right? Because I don't know, it's like intertwined, but also separate, right? So what Roberto says, of course, is what I was also thinking, that as an academic in a Peruvian university, probably my greatest impact, apart from flying every now and then, is on computing, right? So in this sense, maybe would you suggest it would be better to move all of our computing practices to services like Amazon Web Service or something else done by third parties, instead of us, hoarding all of the computers and having to do maintenance and all of the things. Maybe this third party can do it better than us as an individual department. Maybe a third party can do it in a more sustainable way with a much better control. I don't know what your opinion is on this.
Yeah, I think that the question of cloud computing is a really tricky one, and I think ultimately, and this is one of the things stressed in the conclusions of that HECAP+ document, is really assessing the impact is the thing to do, because from institution, from situation to situation, given whatever the requirements are on the computing that you need, what's the best avenue for reducing the impact of that can be different, right? So I think one has to look at various factors when deciding on what computing infrastructure to use, whether to outsource. For instance, looking at whether the third-party providers that you're using have certification, what their policies are, what their credentials are in terms of sustainability, thinking about right sizing your hardware needs, and that's really a question from project to project and situation to situation, right? So I think I think my answer is, I think you just have to assess what actually has the least impact on a case-by-case basis.
We need to do the work.
But the good news is that increasingly people are putting together tools and resources to help try and make these sorts of estimates.
Yeah. Yeah, because it's not easy. It's not easy. Yeah. Yeah. No, there's this. I mean, regarding Amazon Web Service, I attended these talks given by them on the advantages, right? And it's like, oh yeah, it's so great because we handle the air conditioning, if we handle all these electricity bills, and things that you don't initially think about when you're initially saying, oh, I need a server, But anyway, so I don't know if there's any other questions by our guests. We don't have anything from the chat so far, so maybe there's something else. Roberto, you've unmuted yourselves. Maybe
Yeah. I wanted just to kind of continue with this part. I guess maybe we are more worried about the impact of computing, but regarding the last news, I mean, in the sense that also this year the Nobel Prize in Physics was related with the machine learning, and also there are many news saying that in fact machine learning could be very hard to sustain from the size of energy consumption. What would be the because as far as I understand, machine learning cannot be more efficient than what is now. Kind of, I mean, and all the applications are using the part in which they need to train the algorithm, the neural network, whatever, and that is the part that is more energy consuming. And in physics, we use a lot, have been used a lot, the machine learning, especially for training and retraining and training the data set and so on. So this is a point that in the future may be complicated to address, to how to load the impact of the consumption of the machine learning itself, but the impact in science, because it's helping a lot to the development in particle physics, for instance. If you have some
Yeah.
comments on that, because I guess it's an open question, let's say.
Yeah. I mean, I think the one thing to be said is, of course, that people are working very hard to think about efficiency in relation to machine learning. So optimizing training so that you don't under and over train, and optimization of training data set sizes and things. But I mean, I guess what your question gets to is presumably there's a point at which that can't be optimized any further. And I think here that, well, absolutely, this will be a challenge, right? And this comes back to this problem of the this energy gap, right? That if you extrapolate forward the energy that we're going to need globally, while at the same time trying to reduce reliance on fossil, on high carbon forms of electricity, then this just leaves this huge gap. And here I think is really where the sort of do differently phrase comes in, where we have to think very hard about what it is that we're doing and why we're doing it, and what's important and what's not so important, right? Efficiency will only get you so far. We have to think really, we have to really prioritize, and you know, alongside being more efficient.
Great. Maybe we can move on to a part about the large research infrastructure, right? I was very interested by your first plot regarding comparing CERN, Fermilab, and Los Alamos, right? Because okay, CERN at that point was on its shutdown phase, right? So we cannot blame the LHC for the emissions and all of the things. So I was I mean the LHC operation, at least. So I was wondering, you know, that the large difference between the CERN scope 1 emissions and the ones from Fermilab. I mean, why are we having this difference in scope 1? Because scope 1, I understood, was direct emission, right, of gases. So do we know where these emissions come from, and why in Fermilab you don't have any?
So a large proportion of this is gases, is loss of gases from detector and cooling systems.
Oh,
So a huge amount of work is being done at the moment to try and find alternative gases. So to replace the fluorinated gases that are currently used. And the challenge there is that a lot of the gases that you would want to replace them with are proprietary, but also a lot of those gases are forever chemicals. So it's this sort of classic problem that you just keep sort of losing. So we got rid of CFCs, and we replaced them with HFCs and PFCs, but they have a huge global warming potential. So now we want to get rid of those and we'll replace them with something else. And some of the good candidates for replacing those are forever chemicals. So it's this constant battle of trying to find ways that are, there's no silver bullet. There's no simple solutions in this space, right? It's a challenging, multifaceted problem. So there's a lot of work being done on finding replacement gases or gas mixtures which have lower proportions of fluorinated gases for detector systems. Then there's also ways of attempts to change cooling systems. So for instance, actually using CO2 systems for cooling instead of other systems. So there's a lot of work ongoing to try and do that, and also to stop leaks. To fix leaks in existing systems, because when those systems, these detectors were designed a long time ago, so there are lots of nice kits that the experiments have now for quickly sealing leaks of F gases, and that's made a huge difference. But that's certainly an ongoing program to eliminate these gases.
So yeah, since this come from the cooling that will be needed regardless of the LHC being in operation or not, right? So
I guess, in the detectors, right? So
yeah, okay, I understand that. So then the LHC operation will only have an impact of the electricity cost.
I mean, but predominantly,
not on
predominantly. Yeah,
I see.
So it effectively doubles the scope 2 emissions, effectively double when the LHC is running.
And the electricity cost, is it? I mean, because in Fermilab it was very large, right? So then is it only because CERN gets it from France, which has got less impact due to it being from nuclear production? Is it mainly because of this, or is this because of, it's in the USA, maybe they use too much air conditioning? So is it a point of extra, a more efficient use of energy at CERN than in Fermilab, or is it just the source that is a much better source?
I mean, the caveat on this is that so this self-reported data is not necessarily sufficiently fine-grained to know the exact breakdown, but certainly the difference in the energy mix plays a major role in this. So the fact that CERN gets its power from a large proportion of nuclear generated electricity, this lowers the footprint for those scope 2 emissions for CERN.
Okay, we haven't had any questions from the YouTube, even though there are viewers currently. so please, if you have a question, please go ahead, because the idea is to have some discussion. Maybe some of the other guests would like to make a comment or something.
I have another question for Peter, but because also you talk about a large part of the impact that we have like scientists is by traveling, transportation, so on. So in that scenario, because you mentioned that maybe more senior researcher, maybe they can try to travel less because they have already the network, and nowadays we have the tools to collaborate remotely instead of going to going so often, because I remember that when I was in Valencia or in Italy, yeah, we used to travel a lot for conference because there were it's plenty of events all the time, traveling by plane or train, depending of the situation. But nowadays, with this, taking this into perspective, we should try to to reduce our CO2 imprint, let's say. No, but regarding to that, also it's if in this report is also considering the case of that conference tends to be also in the kind of in the high season of tourism, and then increase the travel by force, let's say. I don't know if also there is would be some strategies to put conferences in other period of the year to reduce the impact of the stress of the environment, let's say by hotels and transportation, like local, like cars and public transportation. I don't know if you have thought about that.
Yeah, I mean, I comment on those both of those things. So I think the point I was trying to make was that was not that established scientists shouldn't travel, but that the impact of reduced traveling on established scientists may be less than the impact on early career scientists who are still trying to develop their networks and gain exposure in the international community. Travel is a really difficult one, and it's I always like to use it as an example because it is a microcosm of the challenge that sustainability presents more broadly, because it's something that everybody is able to weigh in on, everybody has thoughts on, and it's something that very much shows this tension between sustainability and equity and inclusivity and diversity and accessibility in the field. And so it's a good example of what a challenge addressing sustainability really presents, because if we all stop traveling, there would be less emissions from us traveling, but there are very real questions about how you maintain a global international community of scientists, which is truly global, right? That doesn't geographically isolate people. So, for instance, if you were to do an optimization problem that didn't take into account human factors on where to put conferences would always be near to where most scientists were. And so if you optimize in that way, you just further entrench geographic disparities in access. So this optimization problem is a really difficult one. And we have to ask ourselves, what is it that we want to achieve through that travel? Is there travel that we cannot do that can be done a different way? But is there bits of travel that are absolutely necessary for the way in which research works, the way in which collaboration works? We also need to move people around to work on experiments. So there are some aspects of travel, the constraints on travel are very varied. So all of those factors have to be folded in if you want to really think about implementing sustainable travel policies. For instance, you have to think about how these travel policies disproportionately affect different groups, whether it be people with caring responsibilities, whether it's people who are geographically isolated, whether it's early career researchers with lower travel budgets, for instance, than more established researchers. All of these questions have to come into play if you want to really come up with a workable and fair policy that implements positive changes with respect to sustainability as well in terms of travel. That one's a really difficult question, but as I said, it's a good example of how many factors one has to take into account when trying to implement changes in relation to sustainability.
Great. I don't know if there's any follow-up. We're running out of time.
To say thank you.
No worries.
We're running out of time, but I'd like to make a couple more questions just in case. So I don't know if you have any information about if this is being done in other fields of science, like in biology or material science or something like this, in other fields where like in our case, as theoretical physicists, I mean, okay, we need CERN, right? We need Fermilab, blah, blah. But then locally, we need a server, and that's more or less it. While maybe biologists, they need their own lab, material science also usually they need their own lab, So there are different costs there that So I was wondering about the impact that other disciplines might have compared to us. Are we the most expensive ones? The ones with most impact, or are there other disciplines that do better, do worse? So what's the situation there? I know you're aware of.
That's a really good question. I definitely don't know the exact numbers for a comparison between fields. What I do know is that the challenges that many fields face is very, very similar. So any field that relies on big data faces similar challenges. And I know that there are efforts across different research fields and interdisciplinary efforts as well, to look at sort of green computing. So yeah, absolutely, it's something that I think all fields are waking up to and addressing. I think this is one of the reasons why I feel increasingly optimistic that we're moving in the right direction, because even since Wheel started on pulling together this Sustainable HECAP Plus document, so that was in the summer of 2021, over that period of 3 years, I mean, it's an almost dramatic transformation in the level of awareness, the level of platform that sustainability now has in the field. In interdisciplinary conferences that I've been to, sustainability is one of the topics that everybody can discuss. And we can't discuss each other's research, but we can certainly discuss common challenges related to sustainability. So this culture change is happening, and that's why I stress this point about tipping points. I think we're pretty close. If we keep driving these small changes, I think we're not far away from really getting to the top of the hill, and then really seeing major changes in the way we think about how we do our science. And this is about finding ways to do the cutting edge science that we want to do better, right? So if we value our science, which I think we all do, and we know that it has a positive impact, right? That we need to be enabling that science to keep happening, and the way to do that is to really look strategically, systemically across the way in which academic research and our fields work.
Fantastic. It's good to end the colloquium with a positive note. Okay, so there's no other urgent question. I think it's good time to close the colloquium. I'd like to thank you once more, Pete, for giving this talk. It's been very instructive.
My pleasure.
And let me remind all viewers that in 2 weeks we keep on with our standard webinars. We will be having Fabian Bautista talking about something related to gravity, most likely. Not really. But okay, thank you very much for everybody around, and we'll be seeing you soon.
Thanks, everybody.
Yeah.